Swayam Prabha. Digital India. Educated India.
Hello everyone. So now we are going to look at experimental setups used for compressible flow experiments. We will start with shock tubes, okay, and then we will go and deal with other supersonic facilities which are existing, because this is also a part of compressible flow experimental setup. So we will start with shock tube, it will add nicely to the other setups. So shock tube, by the way, is a unsteady experimental setup, as in it will work only for a few hundreds of microseconds and then it stops, and in that time it produces whatever supersonic flow if you want, or high speed flows, subsonic or supersonic if you want, and then it stops. Okay. So it is actually a moving shock problem if you think about it. We will go and analyze it now onwards, but before that I want you to recap the problem which we already did on moving shocks. Let us go to the screen. You have seen this animation already. Basically, if I have a piston that is moving in a duct and the gas initially was stationary, then this piston causes a set of compression waves come together to form a shock, and the moving shock is going to move in such a speed and strength P2 by P1 such that it will cause this gas to get compressed and move with the same velocity as that of the piston. Okay. This we have already seen. Now we will go look at another animation where this is the opposite. If the piston goes the other way, then the high pressure gas is now expanded to a low pressure gas, and it is expanded in a slow gradient, slowly. Okay. So there is a big set of expansion fans sitting in this whole region. There are so many expansion waves inside here. The density is slowly decreasing from here to here, and then here the density, after the last wave, the density remains constant. That happens in a expansion wave. Okay. These things we already knew. We did not write expressions for the density variation inside the expansion waves. We did that only for moving shock cases. We did not do this for moving expansion fan analysis. We did not do that part. Okay. But we will use the result from such an analysis. We will not worry about deriving that in our class, because I think it is too much of a derivation. It needs a lot of acoustics expressions to be solved. Okay, it is isentropic. If I think about it, it is actually isentropic flow of a wave in a flow, in a gas. It can be quiescent gas, it can be moving gas, any of that. So it is related to that. So we will not do that particular thing, because that will take around 3-4 classes. I do not want to spend that time on that right now. So what we do is we will just go and pick up expressions that we already derived. So you will remember moving shock problem, where a piston is going this way, velocity up. We did not solve the problem like this. In a way, we solved it as a numerical example in one situation like this. Okay. Initially I said that u equal to 0, actually we used v variable. With respect to the lab coordinates, it was v variable. Okay. With respect to shock coordinates, it was u variable. That is what we used. Okay. This is going to be v, and v1 was 0, and the v2, if there is a shock and the shock is moving with velocity ws, we used. If it is traveling with ws, then the velocity behind with respect to outside lab coordinates, v2 is equal to my up, the piston velocity. That is the job of this particular shock wave. That is the overall idea. And I will just go and write the expression which we already derived. We already said that v2 minus v1 must be equal to u2 minus u1, where these velocities are with respect to shock fixed coordinates, while these are with respect to lab coordinates. We already derived this, and I will just substitute numbers. Oh wait, I put v2 minus v2, should be v2 minus v1. V2 minus V1 equal to U2 minus U1. This is U piston, the piston velocity, minus 0 is equal to, I will pull out minus U1 here, the same thing we did even before, 1 minus U2 by U1. I have this, and this U2 by U1 is with respect to shock fixed coordinates. So, I will go and use normal shock relations and shock fixed coordinates, We have this relation to be rho 1 by rho 2, which is given by gamma plus 1 by gamma minus 1 plus P2 by P1 divided by 1 plus gamma plus 1 by gamma minus 1 P2 by P1. We wrote this expression as rho 2 by rho 1 and this reciprocal. I just wrote it the other way in here in this class. Okay. And of course, you can write T2 by T1 also, but I will just write the simple one, P2 by P1 into rho 1 by rho 2. So, P2 by P1 multiplied by this quantity in here will be T2 by T1. Okay. And finally, we want to find Ws, okay, the shock velocity Ws, I used capital S, it looks like, okay, which is M1A1, where M1 should be expressed in terms of P2 by P1, that is what I wanted. So, I am going to write it as A1, we already did this derivation also in our moving shock case. I just wrote expressions from a few pages ahead in my notes. Okay. This will be the relation you will get. It is basically inverse of that m square term, that is why you get this half in here, just inverting the P2 by P1 in terms of m square, you get to this relation. Okay. Now, if I want to find the actual velocity behind this UP, now I can find that based on this substituted inside here, where this minus U1 is going to be nothing but this velocity, right, Ws. Why? I am having V1 0, very important, I am assuming V1 0. Because of that, with respect to shock, the incoming gas velocity will be equal to the shock velocity with respect to that gas, right. They are standing, my bus is moving. Equivalently, I am going to see that they are coming in this way with the same speed as the bus, same relative example, right. So, that will be minus U1 will be my Ws. So, this is going to be my Ws. Okay. So, now I can find the velocity V2, which is equal to UP, from this relation. Okay. From this relation, I know Ws from the formula here, and I have a U2 by U1 formula here in terms of P2 by P1, that I substitute in here. I can find a UP in terms of just P2 by P1, just one variable. Okay. Of course, there are other variables like gamma, okay. Gamma and A1 will be there. We will keep it as A1, we do not want to substitute it as T1 as of now, okay, because shock tube people want to work with only A1. Now, we will go and do the expansion problem. We saw this animation also, where I am having a piston moving the other way, and I am going to say the expansion waves are already started and they are moving all the way out there. They are going to look something like this. This is the first wave and this is the last wave. This is the last wave, first wave. Okay, I will put 1 and n here, first wave and last wave, and I want to label this state as 1, this state as 2, similar to what we did there. Okay, 1 is before the wave affects the problem and 2 is after the wave affects the problem. Okay. So, this, of course, I am not going to derive this, I am going to say if I solve the problem of isentropic propagation of expansion waves in a gas, I can find this solution. I will just write that final expression here. I am putting this modulus sign because I have already taken care of the sign of that UP. Okay, so only the magnitude needs to be entered there. Okay, I have this expression. I may need this, so I will give this also. Speed of wave 1, that is the very first wave, that is going to be A1. Okay, that is, it is going to move with speed of sound of that free stream gas, the upstream gas. And last wave, speed of last wave, we define this as A2, and I can give an expression based on that analysis, which I am not doing in class. This one. Okay. Because of that much change in pressure due to this velocity, I will end up with a slightly lesser A2, and that is what this is showing. Why is it lesser A2? I am expanding the gas, it is going to be cooling down. So when the temperature goes down, your A2 will be lesser. Okay, this is assuming same gamma as of now. We are assuming constant gamma in here. Okay. I have a whole set of relations here. Now, if I look at this P2 by P1 expression, it looks a little tricky. If you look at it, this to the power 2 gamma by gamma minus 1, this is always going to be more than 1. Okay, definitely more than 1. In fact, it is probably more than 2. Okay. We will keep it as more than 1, that is enough for me right now. Okay. We will keep it like that, but the function inside will decrease with UP increasing. Okay. If my piston moves faster and faster, my P2 by P1 becomes lesser and lesser. Okay. If it is say 1, then my UP is 0. Okay. In which case P2 equal to P1, piston does not move, no change in pressures. If my piston increases, then this is less than 1, which means that to the power more than 1 means it is like square or cube or power 4 or something, that is going to be much less than 1. Okay. So, it is tending closer and closer to 0, this particular value. Now, if I look at this particular expression, this can become 0 exactly when my UP is equal to 2A1 by gamma minus 1. Okay. If you look at this number 2 by gamma minus 1, if I assume gamma is 1.4, 2 by 0.4, 1 by 0.2, it is 5A1. 5A1 is not very difficult for my piston to move, if you think about it. What will happen if I move my piston faster than this one? If I move my piston faster than that value, P2 will go to 0 if it is equal to that value. What will happen if it is lesser? What will happen if it is lesser? That is, UP is more than this 1. This whole function is more than 1. So, you are going to have a negative number to the power something huge. You are going to end up with pressure P2 negative, which is not possible. Pressure cannot be negative if you think about it. So, I am getting unrealistic solutions. Is that right? But you have to think about one more thing. I assumed continuum all through. Okay, that is what is violated when I go past this point. Okay, we will see how. When I make it UP tending to this value, I put it in here, this tends to 0, which means my P2 by P1 tends to 0. If my P2 by P1 tends to 0, now I look at my rho 2 by rho 1, this is equal to similar formula. Of course, you can get it from isentropic relations. Okay, you can get it from isentropic relation between P and rho. You can get to this point. You are going to get this formula, and you can again see when this tends to 0, and this is more than 1 always to the power. So, this also tends to 0. Rho 2 tends to 0 if I am making this equal to this. So, there is a point where my density goes to 0. Basically, the gas is very, very rarefied. It is not in continuum regime, and my analysis breaks down. Okay. So, I cannot be using this expression for UP values more than this specific critical value. In fact, I cannot be using it even when it is close to this value and less. Okay. I cannot be using it for roughly 5A1 for gamma equal to 1.4. I should not be using it for that. Okay. That's just a way of thinking about it. What will happen in real life when I move faster than this? It becomes so rarefied, gas molecules don't even know that the piston is moving, because there is no molecule near the piston. Okay? There is no molecule near the piston, nothing is going to go and hit it and find out that there is nothing, there is no piston anymore. The piston moved out, nobody to go and check whether the piston moved out or not, nobody is around there. Okay? So that information never got transferred. Or another way of thinking about it, the piston moves, there is no molecule there to take the information and give it to the next molecule nearby. There is no first molecule itself, and there is no next molecule either. Okay? So there is no transfer of the wave. So it cannot be rarefied any more than that particular value. Okay? That is what you will end up with. If you think about Prandtl-Meyer expansion curves, you are reaching the ultimate expansion point, m tends to infinity point by then. Okay? If you think about it in 2D case, this is not 2D, this is just 1D. Okay? So you cannot really talk about that in here. Okay? This is just an analogy part of it. Now I have the expressions on the board for whatever I need to do. Okay? Now I want to go think about what I call a shock tube. It is basically a long tube with a thin diaphragm in there, and I am going to put high pressure gas here and low pressure gas here. We will see why one of them is longer than the other, obviously because shock travels faster than expansion waves. Okay? Now the idea is I am going to call this state 1 and this I will call state 4, which means I need not have the same gas filled in these two regions. So I am going to have separately gamma 1 and gamma 4. There can be a A4, A1. Let us assume the temperatures initially are the same. Pressures are of course different, P4 and P1. Okay, they are very different. That is what I have, and I am going to say at time t equal to 0, I am going to puncture this diaphragm there. Somehow I make it crack. There is no more diaphragm. Suddenly the high pressure section of the gas meets the low pressure section of the gas. What will happen? It is like opening the gate at the stadium which is crowded and outside there is nobody. There is going to be a whole set of people running out, and an expansion wave travels into the stadium. We already talked about this problem. And what happens to the outside world if there is some people standing there? They are going to be pushed out more away from the gate. Okay? So what is going to happen in here is there is going to be an expansion wave that will go in this way. If I look at only the high pressure gas section, it looks as if there is a piston that moves out at some speed, I do not know what speed as of now, at some speed such that expansion waves will keep traveling here and making things adjusted to the other section. Now I will look at it the other way. In here there is a huge high pressure gas sitting here, and suddenly it is going to be pushing at t equal to 0 onwards. Okay? If it is pushing against this low pressure gas, then I am going to have the other problem of a piston traveling against the flow, and thus going to develop a shock, and the flow is going to go behind it this way. Okay? So overall what is going to happen in here? I am going to have a shock traveling this way and a set of expansion waves traveling this way. Okay? Let us draw that case as a function of time. This is my time axis. This is typically how they represent a shock tube dynamic. I am going to represent things in x versus t plot. Okay? And let us say this is my t equal to 0 line, this bottom line, and at t equal to 0 let us assume that the shock instantaneously formed, which is not really true, we will come back to it later. It is instantaneously formed, let us assume, and it is traveling in a constant speed. I am going to say it is traveling in a constant speed, dx by dt is a constant, so it is a straight line slope thing. Okay, it is just straight line, and dx by dt will correspond to that speed of that shock speed. We already have expressions for it anyways. Okay, we will get back to it later. On the other side there is going to be expansion waves. We said initially the temperatures are the same, but A4 can be different from A1, I said. Okay? Even if the temperatures are same, T4 and T1 are same, A4 can be different from A1 because gamma is different, maybe R is also different, okay, R can also be different, okay. We will keep it that way, okay. Typically R4 is far greater than R1, that also happens in there, okay. So now if I think about what is happening here, this shock is traveling at this speed. If I think about any particular particle that was sitting at this location, let us say that was here, it is going to be sitting at the same location till some information about this diaphragm breaking comes to this point. What is the first information that comes to that point? It is the shock, okay. The shock is telling that there is a high pressure section, run away from there. So till that point that gas element just sits there. So I am going to say it will be sitting there as a function of time. After the shock it is going to travel at some speed, but definitely less than the speed of shock, right. So it is going to be going something like this, okay. That is what will happen in this case. Now I look at some point in here. Again this one does not know that there is low pressure on the other side immediately at t equal to 0. It knows it only when the first expansion wave comes and touches this. Then only it thinks about starting to move this direction slowly, okay. So I will put that point in here and it stays at the same location till the very first wave traveling at speed A4 comes and touches that. After that, since it is an expansion wave coming this way, what will it do? It will induce a velocity the opposite direction. So this point, this fluid element at that point will want to travel the other way. Expansion fan will go this way to the left and the fluid element will want to go to the right. So it will start going to the right and it will keep on accelerating towards the right only up to the last expansion wave. After that things have come to equilibrium, it does not want to change anymore, okay. Now I will ask this question, are these two lines parallel? I have drawn it in some way, I do not know whether it is really parallel, it looks like they are not parallel. What will happen if they are not parallel? This fluid element will go and crush the other fluid element. If that happens, what is really happening? This fluid is still pressing on that fluid, so there will be one more extra compression wave created on that fluid, which will go and increase the shock strength till it becomes equal and parallel. That is one way of thinking about it, okay. Maybe the other thing might happen, maybe this thing is going far away like this. If it is going out like this, very low velocities, dx by dt is less, that means it is almost vertical, it is going like this. If it is going like this while that one is traveling faster, what will happen now? There will be empty space created because the fluid element here and here are now diverging, the space in the middle will be empty. That means there will be expansion fans from here going all directions, okay. Expansion fan from here going this way will tell the fluid to go accelerate and fill that space, so the fluid will turn this way. Expansion fan going here will go and decrease the shock strength so that it does not go that far, but it will go a little more like this. So it will go to a point where it will finally have a nice equilibrium of these two velocities being exactly equal, that is these two lines are parallel. Till that time it is not a stable system, and all this happens in this small region itself, which I am not going to discuss too much. I am going to assume it is a single point and everything is already discussed and assumed, fix it, okay. Fluid element immediately calculates all this and puts it out there, that is what we will assume, okay. That is a small assumption, it works reasonably well for our cases, we are not interested in that small time scales, okay. In a very short time, probably within a microsecond or two, all those strength, the strength of the shock, how much expansion fan should be there, all that are all decided within that time. Okay, and finally what should be the velocity of the fluid element behind the expansion and behind the shock, everything is set by them, okay. Ideally it is not set when it is this far, it is set for that particular fluid elements very next to these diaphragms. Immediately after that, this wants to go this way, while this one wants to turn and go this way. If they are not going parallel, then they will interact and send out extra waves this way or that way to make it equal. Okay. So now I arrived at a particular condition for my flow, which is similar to what we did in 2D gas dynamics. We said the velocity direction should be the same for both the fluids and the pressures must match. Okay. Did I talk about pressures really? Not yet. Let us talk about pressures again. What if the pressure on the compression side is higher than the pressure from the expansion side? What will happen? Then this pressure is higher than this pressure, there will be a compression going this way. What will it do? It will go and decrease the expansion strength, and equivalently the other side will have an expansion which will go and decrease the compression strength. Then this strength will decrease, this strength will decrease, eventually it will come to a point where it is higher pressure after expansion and lower pressure after compression, that they both match now. You can now argue for the other case where it is the other way. Okay. It will work correctly. Okay. So I just gave arguments. Now I just have to label these parts. I labeled this 1, 2, 3, 4, right? Oh, I labeled it wrongly, it looks like. Okay. Oh, this is the correct labeling. I labeled it in my notes wrongly. Right? In my notes I have it wrong. This is the correct. 1, I will call this region 2, this region 3, this region 4. As of now I did not discuss the difference or the boundary between these regions 2 and 3. Let us assume I have gas 4 different from gas 4 different from gas 1. If I assume something like this, now what will happen? That is the next question. Okay. We want to think about this. If this gas is different, they are both going to be traveling at the same speed. We know that already. We just figured out that u3 equal to u2 and p3 equal to p2. We know these two things already. If they are traveling equal, then the boundary, if I draw a boundary between these two, that is the immediate fluid elements next to the diaphragm on either side, they will both be going parallel to each other, and I will just draw that line here. Okay. I will just draw that line, and that line should be going exactly parallel to this u3 and u2 lines. Okay. Now I am calling the region 2 as the region where the gas that was processed by the shock is present, and 3 as the region where the gas that is processed by the expansion waves, all the expansion waves together are present, and region 4 is untouched and in the high pressure section, region 1 is untouched and the low pressure section. This is what we have. Okay. So now we want to see what these values are. Okay, that is the next step. I want to find what will be the velocity in this region, u3 and u2, what are the values, that kind of relations. Okay. We can find the values, it is not very difficult, we already know stuff for this. Okay. If I know the shock strength, I can give you u2 by u1. We did this as a moving shock problem and I wrote the notes today on the board anyways. Okay. And similarly from here expansion, if I know the strength, I can tell you what will be the velocity u3. Okay. So all we have to do is go and write expressions for those. u2 is equal to a1 times p2 by p1 minus 1. I have done some rearranging of terms which I do not want to discuss here. I believe you can get to this point with a little bit of algebra, it is not very complex. If you look at the formula there, it will be easily rearrangeable to this form, not very difficult. Okay. This is coming from the moving shock expression. Now I will write another for u3, the expansion side, okay. And that expression Now I am writing, I am being careful about the gamma. I am saying gamma 1 and gamma 4. Remember that. Okay. Now I want to say I will enforce u3 equal to u2, which means I am going to equate these two expressions on the right side, and I will again say p2 equal to p3. So I will replace this p3 with p2, then I will see what I end up with. Okay. It is 1 minus a fraction. It is a big expression. This is why I did not want to derive this whole thing in class, because that itself will take probably half the class. Okay. We do not need to derive this, it is not that important for our course. We just need to know that it changes in some particular way. Okay. Now I have P4 by P1 in terms of P2 by P1. The way I want to look at this expression is, for a given gamma 4 and gamma 1 and A1 and A4, that is I pick the gases 1 and 4. If I want a particular P2 by P1 across the shock, then I have to choose this particular P4 by P1. Okay, that is the expression I am having here. Okay. It is better to express this in terms of Mach number, because then after that it is easy for us to calculate velocity behind the shock. It is a moving shock problem. After that we know how to solve that problem. Okay. So I will rearrange this. P2 by P1 can be substituted for M1 from P2 by P1 relation, we already know that. So I will just substitute that. Of course, again I am not going through the full derivation. Gamma 4 minus 1 divided by gamma 1 plus 1 times A1 by A4 times M1 minus 1 by M1. This whole thing to the power same thing, minus 2 gamma 4 by gamma 4 minus 1. I have this big expression. Very useful expression in shock tube analysis. Okay. Now I have decreased it to a little bit easier expression. It still does not look very yielding expression. Okay. If you look at it, there is M1 and then the properties of gas 1 and gas 2. Those are the things that I have. If I want to create a particular Mach number M1 with the gas with property of gamma 1 and A1 on the low pressure side and gamma 4 and A4 on the high pressure side, then I can use this expression to find what should be my P4 by P1. That is what I have. If I set these two pressure values here across that, only what matters is only the ratio. Okay. Typically I do not need to have very high pressures. What they do is they make it more and more vacuum so that I get this ratio easily. P4 by P1 is obtained by decreasing P1 very well. Okay, we will go the operation of it after understanding what happens exactly. Okay. If I think about, I want to have very high Mach number, what should I do? From physical feel, I will go look at this picture, it is easier to think about. I want the shock here to travel very fast. What should I do? The jump in pressure should be really high, right? Then it will say, the information that is traveling will tell, oh, run extremely fast, okay, because there is so much crowd there, nobody there, just run extremely fast, that is what it will tell. Okay. So, just by physical intuition we will keep that, it will help us a lot. Okay. So, I want to say, I want to have maximizing my M1, what should I do? I will go here and say I want to maximize this P4 by P1. I look at this expression, not much under my control, they are all gamma 1, only thing is M1. If M1 increases, P4 by P1 increases, that does not tell me anything new. So, I look at the remaining expression. This one has ratio of A1 by A4, gamma 4 by gamma 1 kind of ratio is there, and M1 minus 1 by M1 is there. If I say M1 is very large, I am going to neglect this 1 by M1 with respect to M1, very nice to neglect. Okay, think about 5 itself, I can neglect this term. 1 by 5 is 0.2 compared to 5, 0.2 is very small. Okay. So, if M1 is 5 itself, I can neglect it. If I think about M1 going to 10, 15 and all, I can definitely neglect this number. Okay. So, let us say I neglect this part also. Now, I have an expression that is 1 minus this fraction times M1 to the power minus this thing, which we know, we already saw this kind of formula somewhere back, where we know that without the minus sign this is always more than 1. So, this is this square bracket reciprocal to the power something more than 1, that is what I have, and I want that whole expression to go to infinity, right, I want it to be maximized. So, I want to make sure that the square bracket tends to 0, that is the idea. I want to make the square bracket tend to 0, which means this ratio, this expression, the second term must be almost equal to 1, that is what you have to think about, we will make it equal to 1. Okay. If I think about it that way, I have to say that my M1 must tend to gamma 1 plus 1 by gamma 4 minus 1 times A4 by A1. Okay. This is what I will have if I want to maximize my Mach number, then the maximum Mach number I can get will be just this. Okay. If I want to produce a very high speed U2 or U3, of course you know U2 and U3 are the same, if I want to produce high speed of flow behind the shock, then I want to maximize this M1. If I want to maximize this M1, now I have to think about maximizing this quantity, that is a way of thinking about it. Okay. It will be the maximum for whatever this value, but I want to maximize even this. If I think about it that way, then I am going to say I want to have gamma 1 high, gamma 4 small, right, or better yet I want to have A4 by A1 high. Okay. I will write A4 by A1 high first. But think about this, this also has gamma 4 by gamma 1 inside, of course having a square root on it, that is also inside this. We already assumed that T4 and T1 are the same. So, the main ratio happens to be gamma 4 R4 divided by gamma 1 R1 whole square root, that is what this expression is. Okay. So, if I want to maximize this, I can also think about one more possibility, gamma 1 by gamma 4 high. I will say this is not as important as this one. Yeah, I will say this is more, the first one A ratio is more important than this one, this is not important. Okay. I will say if you want to think about it, gamma 4 less than gamma 1 helps, because both of them may not be achieved all the time. Okay. How will I make this speed of sound at 4 very high compared to speed of sound at 1? Molecular weight is a good way of doing things. Okay. R, gamma does not change much across gases, it is going to go somewhere between 1.2 to 1.66 for all the gases, it is not going to change a lot. Okay. That is why I am telling this ratio may not be very interesting. More interesting is to look at this one, A4 by A1. Okay, if I think about it that way, I want to maximize A4. What should I do? I will look at R. R for the gas is universal gas constant by molecular weight of the gas. So if I want R4, it is molecular weight of 4, whatever gas at 4. So if I minimize molecular weight, I will get maximum. Okay. So typically people use helium for this. Helium is really light. Okay. People can use helium and now they will say, yes, I will get very high A4. Okay. A1 typically should not be helium, right? We want it to be as high as possible in molecular weight so that A1 decreases a lot. Again, along the same direction, I want to think about A1 should be having higher molecular weight gas. But based on the application, typically we will not have the luxury of changing the gas at 1. Okay, we will see why next class, probably in 5 minutes probably. Okay, we will have only the luxury of changing this. Because most people use this particular shock tube for changing the pressure and temperature of a gas suddenly to a new value. Okay. So if I want to think about that, this particular gas 1 is our test gas. That is what it will be typically. Okay. So if I think about it, I am going to use helium on the high pressure section, and on the low pressure section I will use whatever test gas I need. The next things I need to do will be go and observe what will really happen there. Okay. Oh, I will start with this picture again. I am here, I have put some gas inside here. Let us say typically the people who are using this will be chemistry people or combustion people, people who want to study reaction rates. Okay. Shock tube, if I just want to use the plain shock tube, it will be used by people who are in reaction rate determination kind of people. So they will have some reaction mixture which they want to study in here, and then probably very low molecular weight gas here, depending on what P2 and T2 they want. They will work with that. Okay. And they put it in here, they give the shock, and then this whole situation will just, all this gas will get compressed and go to this corner. By the way, what happens when the shock goes to the end? We did this problem already. It will reflect back at the end wall. I am saying it is a closed tube, so it is going to reflect back from there. Okay. So if I think about it, I will draw a dotted line. The shock goes there and it turns back. When the shock turns back, I will make this. Oh, by the way, this boundary between 2 and 3 regions is called a contact surface. Contact surface. Okay. So shock, when it reaches the contact surface, after that the shock makes sure that the gas in region 2 will come to stagnant point. This is region 5, by the way. Okay, comes to stagnant point, which means my contact surface will now go straight like this. I won't worry about what happens in this region after that. Okay, currently we will just say the shock just goes straight. I won't worry about this right now. I will talk about this probably next class. Okay. As of now, it is just going straight, and region 5 has stagnant gas. So I have finally taken my gas at 1 to state 5, just T5 P5, and now I can study suddenly pressurized gas and at a very high pressure and temperature. Okay, it has been processed by 2 shocks, and all this is happening in microseconds time scale. Okay, within say 100 depends on the length of the tube, of course. It could be anywhere in the order of 100 to 500 microseconds. Okay. So that kind of time scales. Within that time it got compressed. Now I can sit and wait for some time. I have some time before the expansion from the other side. Think about this. Expansion goes and hits this wall. Now this will want to reflect back. And of course the first wave and the last wave are going to be diverging as it is. this will eventually come and reach this. I have curved it more so that it does not go outside the board, but if you think about it, this will reach slightly out there. If I have designed my shock tube correctly, it will reach slightly after, and so I will get some time in this region 5 where there is no disturbance. Okay. That is where people will do the experiment, and then people will start observing this region somewhere close to the end. That gives the maximum time, and they will start observing what is happening in there at that new pressure P5 and T5, and now they will do this chemistry reaction rate experiments. They suddenly take this reaction reactants from T1 P1 to T5 P5, and then they will study what happens there. Is it really sudden? Yes, it is. If I think about this particular particle sitting here, this particular fluid element at this location, that fluid was sitting at P1 T1 for this long a time, and within a short time it got compressed and it is now sitting here. Okay. This is all the time it had. Shock is traveling supersonic, remember. Okay. It is going this way supersonic, and then it is coming back supersonic. Okay. So the whole thing together, it is going to be very short time, and if I am thinking very close to the end of the tube, probably a few centimeters, supersonic speeds, it is going to go within a microsecond or so. Okay. Of maybe think about 20 microseconds at most, going to be compressed within 20 microseconds. Now I have increased it suddenly. Now I will study what is happening to the gas. It is going to react, probably it is going to burn. If I put hydrogen and oxygen in that gas 1, then it is going to start burning and producing water in there, or probably H2O2 also. Okay. If you are in combustion, then you will know that they study this H2O2 reaction systems in basic combustion books also. You will see this. There they have come up with all these reaction mechanisms that comes from these kind of studies. Okay. That is a parallel use for this shock tube. We want to understand the gas dynamics part of it, and then we will see how it can be used for compressible flow experiments. Okay. That I will deal with next class. Currently I just want to look at the simple section up to this particular time, whatever this time is, up to this particular time, t equal to 0 to this particular time, no changes, right? It is very simple flow. Okay, this wave wants to go this way, that wave wants to go that way. I want to understand and look at pressure along the tube at all points in the tube. If you think about P versus X, I want to plot. I am putting some dotted lines corresponding to the diaphragm original location and the end wall, and the other end wall is this axis itself. I am having this situation. Let us say I will pick this time T1 at t equal to T1. I will draw a line so that you will know where we are references. I do not need to draw it anymore, there is nothing there. So if I look at it, there is expansion between these 2 points, and there is a shock somewhere here, and there is a contact surface there. These are the key points. So if I tell you that P4 is somewhere here and my P1 is somewhere here, I can tell that before the shock this whole region is my P1 value, and before this first expansion wave all this region is P4 value. Okay, this is your P4 and that is your P1. Now we know after the shock the pressure goes up, but it cannot go more than P4, right? It has to be something in between P1 and P4, because P4 is the one which is causing the shock. Okay. So it will be something intermediate, and then I know that is the P2 value, which is same as P3 value, goes all the way till there, P2 equal to P3. This is what is happening there, and this particular location is the contact surface location. And due to expansion, I did not give you proof for this, I will just tell you that the curve looks like this. The very first wave causes a lot of change because that is the wave which tells that there is a huge pressure difference. And after that the pressure drops a little bit, the next wave comes and tells the pressure difference is a slightly lesser value, because that is what it sees, that is what it perceives. Okay. So, it drops drastically when it is the very first wave, and then it goes gradually down, it asymptotes at the last wave. Okay, that is what you will see, comes like this and then it becomes this. Okay. This will be your pressure as a function of distance in my shock tube at time t1. Let us say I will do another time somewhere here, t2. If I think about that, okay. Now I will tell my expansion reached a lot of distance, contact surface went somewhat this much, shock went somewhere here. Those are my points. Now I can draw P4 should be exactly the same value, and before the shock it is always P1. And we know the shock is the same strength travelling all the way through. So, that is also P2 jump is also exactly the same. And then this whole region is my P2, this is my contact surface location, and till here is my P3. P3 equal to P2 of course, and this becomes my pressure profile in my shock tube. What is happening is, there was initial condition, what was it? It was a sudden step from P4 to P1 at time t equal to 0. After some time this has developed a shock and the pressure is something in between P4 and P1. It is trying to come to some equilibrium between these values. It is coming to something in the middle, and then this whole region is becoming that value, and this side it is going this way, and you can notice that this curve is now less steep compared to the previous one. Why? The expansion fans are going apart, expansion waves in the expansion fan are going apart from each other. So, they are going to split out slowly like this. Okay. We will go deal with more stuff after this next class, okay, where we will start thinking about what happens to velocity at these times, and then we will think about other values like temperature, what happens to temperature. Okay. And then we will deal with what happens when the flow reflects at the corner, okay, that is times more than T2. So, I will also show you probably an animation of this, which is what is missing at this moment. Okay. See you people next class.